So I want us to talk now about the first derivative test and what can be deduced from the first derivative test, and can we actually combine what we studied on local extreme local extreme values, in other words local maximum and local minimum, and actually the first derivative, what can actually be said. And also, can we talk about the second derivative and what can actually be said in conclusion, or when we are combining the local extreme values and also the second derivative, and also what is actually important to find some of the important information about plotting a function. So those are the things that I want us to talk about in this short lesson. So what is important here, if you forgot, we said that if, let's say, you have a first derivative with respect to x and you know that it is greater than 0 on an interval, then you know that the function is increasing, then f is increasing in that interval. That's what we actually said. Remember, in one of the lessons we actually talked about this, and we also said that if the first derivative with respect to x is less than 0 on an interval, then f is decreasing. So it is actually coming down, decreasing in that interval. So we have an interval there. So that is actually one of the things that are actually important that I want you to actually note down. What is actually the first derivative? In other words, what does it actually mean for us? I want you to realize something here. If, let's say, I have some point here, this is let's say I have a function. I have a function and I have a point here, and I am going like this and then coming down. This function from this point, it is actually increasing. Let's say this point here is my point C. So if, let's say, I'm looking at this function is going up, up, up. In other words, it is increasing up until it arrives there. So when the function is increasing, the first derivative is actually bigger than 0. So we're actually having the first derivative bigger than 0 here. And then when you're looking into this one here, this function is actually decreasing. In other words, the first derivative is actually less than 0. This one, we have a positive first derivative. Here we have a negative derivative. So if you look into this function, this is growing, and then it comes there, and then when it starts here, it changes the sign. So at this point, when the derivative is positive, so it starts to change to negative. So this point here, we're supposed to end up having a local maximum here. And then in the other case here, when you are having this here, you can see that I have a point here. I have my point C, and this function is decreasing as I'm going to this point. It is decreasing. In other words, I have the first derivative with respect to x is negative, and then here it is increasing. So I have my first derivative being bigger than 0 or positive. So what is happening here? The first derivative is actually changing its sign at this point like that, but now we're actually changing from negative to positive. Here we're changing from positive to negative. So whenever you're moving from negative to positive, you must know that you are actually having a local minimum. So we have a local minimum at that particular point C. So that is actually what I want us to actually realize. And you can see here you have concave down to end up having a local maximum. In other words, there is something that can be said about this point. If let's say the first derivative is equal to 0, because here the first derivative is equal to 0, here the first derivative is equal to 0. If the first derivative is equal to 0 and you are also having the second derivative negative, in other words, you are having a concave down, you can see that we have a local maximum, and then here the second derivative is going to be positive and the first derivative at this point is going to be 0, so you are actually having a local minimum. Let me write what I'm actually saying, what I've been saying, so that you can actually take some notes. That is what is important. Almost in most of this lesson, we are looking at mostly we are looking at the theory and how to do things, and the examples. We'll start doing the examples when we are actually starting to do lecture 44. For now, lecture 43 is all about the theory side of things, so that you don't only focus on actually doing problems after problem. I want you to at least see the other side, even if you're not seeing it clearly, but there must be something that you are seeing at least on the theory side, so that in the multiple choice you don't struggle. So I want us to talk about the first derivative test. So we said that suppose that C is a critical number, and we said the critical number is like this, is whereby the first derivative is equal to 0, the x value whereby the first derivative is equal to 0, or it is undefined, or the first derivative does not exist. So that x value, suppose C is a critical number of a continuous function. So you must have a continuous function. Let me call this function f. Right. If f prime changes from positive to negative at C, then f has a local maximum at C. What does this simply mean? F of C local maximum value. That's what this thing is saying. Once you can see that the first derivative is changing from positive to negative, increase to decrease, so we have a maximum there. The second thing that we're actually having here, if the first derivative is actually changes from negative to positive at C, at some x equal to C, then f has a local, must have a local minimum at C. In other words, f of C is a local minimum value. So that is what is important. And then the last one is, if f prime does not change sign, does not change sign at C. For example, f prime is positive. It is positive on both sides of C, or let me see this, negative on both sides of C. Does not change sign. Okay. Then has no local maximum or local minimum at x is equal to c. So that's what I want you to see here, is that if, let's say, you remember the example that we took, that whenever you have a function like this, let's say my f of x is equal to x cubed, and we know that this function is usually increasing like this, and then it goes like that. And when we are taking the first derivative of this, you find out that f prime of x is going to be equal to 3x squared. And then, of course, when I'm setting this equal to 0, I find out that f prime of 0 is equal to 0. So basically, 0 is a critical, is one of the critical numbers, because by definition of a critical number, we just said that we wanted the first derivative to be equal to a 0, or we also want it to be undefined. That is what we actually said when we're defining a critical number. But now, when x is equal to 0, which is this point here, when I'm looking at the first derivative before that, looking into this one here, x squared, when I'm plugging in a negative value here, once I square it up, I'll get a positive. Positive times 3 will be a positive thing. When I'm plugging a positive thing, I square it up, I'll get a positive thing times a positive thing. So this one is always going to be positive. So when I'm picking a point here before 0, you'll find out that the function is increasing, and after 0, it is also increasing. That is why this point here is not a local minimum, and it is not a local maximum, because the derivative is not changing. The sign of the derivative is not changing. This one is always growing throughout. This one is not a local maximum, it's not a local minimum. That is what is important here. And then we talked about this one, saying that there's nothing happening here. So okay, now let's talk about something else, which is saying this: how to find the interval where the function f is increasing. The function f is increasing, and where the function f is decreasing. Function f is actually decreasing. So the first thing that you actually need to do here, you just need to find the first derivative. That's the first thing that you need, derivative of f. That is, find f prime of x. So that is the first step that you need to do. The second step is set f prime of x to be equal to 0, right? And then after that, you solve for x. So that's how you can actually find the interval whereby the function is increasing and whereby the function is actually decreasing. And then the third one here is this. So you can set this equal to 0 and solve for x. And then the third one is you want to find the values of x where f prime of x is undefined or does not exist. Okay, why this thing is actually important, because in most cases you'll find out that this is what is specified for those people who usually even pay time to what you need to do. So if let's say you are having a fraction and then you are looking for those values that will make the denominator equal to 0. In other words, you will end up getting an indeterminate form, or you are looking for those values that you will get other indeterminate form. That is what is important here, whereby the function is undefined. The first derivative is actually undefined. That is what we mean by this. Most of the cases, I usually say that if there are such values, you want to look for those values that will actually either give you a number over 0, or you will end up getting maybe something like let's say negative infinity. Let's say you end up having log, let's say you have some base here, but inside here you end up getting a 0. You know that log of 0 is undefined. All those things whereby the first derivative is not defined. Either you have a fraction or you have those functions that are not defined on certain values, like a tan function or something like that, whereby you are actually having an undefined when you're plugging certain values. So you are looking for those values here where the function or the first derivative is undefined. And then the fourth thing that you actually need to do now, you draw a number line and mark the critical values. So what we are actually talking about here, when we are finding critical values, is whereby the first derivative is equal to 0 or the first derivative is actually undefined. So you draw the number line, you have a straight number line, and then after that you place those critical values as either it's defined or it's not defined, but we want them to be placed in a number line. So that is what you do in step 4. And then once you do that, while we're still in step 4, right, then you pick a value. So let's say these are your, I'm gonna call them A, B, C, D, E, and then after that you pick a value. So what you're gonna do, you will pick a value in this region here. So pick any value that you can like to work with here, and then pick a value in each region, right? So you're gonna pick a value in this region and plug it in F so that you get an output. You get an output. So that's what you do. So once you pick a value here and then you plug it in F, then you will get an output, and then all you care about, you want to check what is the sign. Is it positive or is it negative? That is what is important here. You pick a value so that you can check if this is positive or negative. You pick a value in between here to check if it's positive or negative. You pick a value here, you check if it is positive or negative. That is what this thing is actually saying. So that if you are having, let's say, a positive here and a positive here, you can see that, okay, in this particular point here, this one is either just an undefined or a 0, but you are actually not having a change in sign throughout up until you arrive here. So that's what you are actually doing. You want to check the sign. And then once you are done with that, you go to step number 5. So step number 5 is saying that then the open interval, the open intervals, so you have the open intervals will tell us where the function is increasing and where the function is decreasing. Right, so basically, if let's say in this region here you have a plus, this plus is saying the function is increasing here, right? If here you have a negative, then it means the function is actually increasing. No, it is decreasing actually. So we have a decrease here. A decrease. So just a quick recap. So first of all, you find the first derivative. After finding the first derivative, you look at where this first derivative is equal to 0, and then you get those x values. And then after you have done that, you look for the values of x that are making this first derivative undefined. And then once you do that, you draw the number line of the first derivative. It's not the number line of f. And then you place these critical numbers here. Once you have these critical numbers, you pick a point here and you plug it in f prime, or the first derivative, because this one is the number line of f prime of x, not f of x. So you are plugging here in this f prime of x, and when you're plugging it there, you're not only caring much about the output, the value. You want to see if are we getting the negative or a positive. If we have a positive, it means that the function is increasing. If we have a negative, it means the function is actually decreasing. And then you can collect those pluses. If let's say here we have a plus, you have a minus, here you have a plus, then in this region here, you know that the function is increasing. This region the function is increasing, this region the function is increasing, but in this region here between a up to b, you have a decrease, and then here you also have a decrease. That's what we mean by actually step 5. For instance, here if you look into this one here, you can see that if you move from negative infinity up to a, you can actually see that actually the function is actually increasing. So we have an increase there. And also if you look into this region here, you have a B and then you have a C, and then if you look into that region whereby you have a B and you have a E, you can see that the function is increasing in those intervals. That's what we mean by 5. You collect all the information that is actually displayed in this number line in number 4. So that's what you actually do. And then what is actually basically happening now is that if let's say you ended up having to plot a curve, you will find out that just understanding that the function is increasing here, decreasing here, is increasing in there, what is the type of increase? Is this function increasing like this, or is this function increasing like that, or this function is actually increasing like that? So we don't know the type of increase. That is why we need the second derivative test to actually tell if are we here, are we there, or are we there. And also the decrease is the same. Are we decreasing like that? And also at the same time, are we actually decreasing like that, or are we actually decreasing like that? So we have to know which type of decrease. That is why we need the second derivative test to actually being able to say we have plotted a curve and the curve is actually moving in this particular fashion. Another thing that I want you to realize here is this. If let's say you were to plot a curve, there is this thing that we were telling you back in the days. It's not like it was wrong there, it was good for you because we wanted you to understand that much at that particular moment. Of course, here we wanted to expand. So if you look in this, let's say you have y here, you have x this side, and then I'm giving you some function. Let's say this function is just y is equal to f of x. So what we use to tell you is that pick a point here and then you plug it there, you get an output, and then pick another point there and then you plug it there, you get an output, and then pick another point there and then you actually get an output and then get another output there. So if you look into this function, into that function, we said that then you must know that your function is actually smoothly increasing like that. We just join the points and then you will get a nice curve. But the question is now, who said that curve is smooth? What if this curve is looking, let's say is looking something, because you just picked the points, it's looking like it's a straight line up to that point and another straight line there and another straight line up to that point. What if we are getting something like that? We don't know. And also another thing, when you're picking these points, what if the function is actually going like this to that point, and then from that point it's going like that, and then from that point it's a straight line? We don't know. We cannot just say by taking points and then plugging into this function and then evaluating in a calculator we get those and then we can get a smooth curve. That's not 100% way of actually plotting a function. That is why you need to be good with analysis of a function, so that you know exactly that this is the shape of my function. It is increasing, but is increasing in this particular fashion. So that is why we need the second derivative, and also talk about what we call concavity. So let me write it down here. I want us to talk about why this is not writing now. I want us to talk about concavity, and then after that we'll talk about second derivative test. We said that if f(w) prime of x is bigger than 0 for all x in some interval, in the interval, let me call the interval I, right? Then the graph of f is concave up. In other words, if the second derivative is actually, so we're actually getting something like this, right? And then if the second derivative with respect to x is less than 0 for all x in the interval, in the interval I, then the graph of f is concave down, right? And concave down, it means that we have a sad face, so it is going like that. That is actually what is important here. You have to know that. And then of course, if you want to characterize a certain the second derivative test, let me write it here first. We have a second derivative test. So we have this nice thing here. So basically what we are saying here, suppose we have f(w) prime is continuous. So we have, this is not continuous, we have continuous. So we have f is continuous near point x is equal to c. So that is what is happening. So if the second derivative, let me not start with that. If the first derivative is equal to 0, right, at this point c, so we have f prime of c is equal to 0, and I know that the second derivative with respect to x at that point c is bigger than 0, this is what is happening here. At this point here, I have a point here, right? And at this point, I know that the first derivative is equal to 0, so the function is not changing there. And then the second derivative is actually bigger than 0. In other words, we have, at this point, we have concave up. So what is this thing saying? It's saying that here we have a local minimum. So that is what this information is saying. And f of x, then f has a local minimum at c. So that is happening. And if f prime of c is equal to 0 and f w prime at c is less than 0, that's what we're actually having here, then the function f has a local something. Let's evaluate. So at point C, let's say this is my point C there, right? And then I know that the first derivative is equal to 0. In other words, at this point, the function is not changing at all. There is no change. But the second derivative is less than 0. In other words, we are having a concave down. So the function is actually concave down like this. So that is what is happening at that point. So this function actually has a local maximum at x is equal to c. That's what is important here. So once you go up, you will know that actually there must be a local maximum at that particular point. What is important now is this. I'm just gonna write these few things and then I'm gonna call it a day, and then we'll stop this particular lesson. So the question is how to find, this is not how I want to write, how to find the interval of concavity. So we want to find the interval of concavity. There are a few steps, and actually they are, I say there are 5. First thing is how to find that. I'm gonna write them green. So the first thing that you need to do is very simple. Find the second derivative. You find the second derivative, fw prime of x, right? Of f. So you will find the first derivative and then find the first derivative of the first derivative, which is the second derivative. And then the second thing that you need to do, set fw prime of x to be equal to 0. So once you set that equal to 0, then you will be able to find the point of you will find the x coordinate of the point of inflection. So you set this equal to 0 and solve for x, right? That is, find the x this is not the coordinate here, the x coordinate of the point of inflection. Remember that the point of inflection is whereby the function is changing concavity. So you will find that. And then once you do that, the next thing I'm gonna write it in red, right? Find the values of x where fw prime is undefined. So you want to find those values where f double prime is undefined or does not exist. Usually, the reason I usually end up putting this does not exist is because when you're finding the derivative, the definition of these derivatives came from finding the limits. Sometimes when you're evaluating the limit, you'll find out that it does not exist. That is why I am adding this thing here. And also this undefined thing, if you're actually having those functions that are not defined at single points, or when you're having a function whereby it has a denominator and you know that the denominator, you don't want it to be 0, because once you get a 0, you get an indeterminate form or an undefined. So you find those x values whereby this second derivative is undefined or it is actually does not exist. The second derivative does not exist. The fourth step that you need to do, you draw the number line. Draw the number line. Right. So you want to draw the number line, and in the number line, and mark the x values found in so these values, want to find the x values that are found in step 2 and 3. Then once you do that, remember that you'll get something like this, and this number line is for the second derivative. Please make note of that. It's not for the original function. And then you plug those values. I'm gonna call these values a1, let's say this one is a2, and then I have a3, and then I have a4, and then I have some a5. So if I have these things here, the next thing that I want you to do here, I want you to pick a point in each of these regions, the point that you like to work with. So you will pick a point here. Once you pick this point, you plug it in this function here, not f of x, right? So you plug it in this function. Once you plug it here, you will get a value. That value, I don't care what is the value. I want to know that is it a positive or is it a negative. So if it is a negative, what that is actually saying, in this interval starting from negative, starting from a1 all the way this side, the function is actually concave down. And then if this one, let's say, is positive, the function for this one, we know that it means the function is actually like this, and then positive means the function is like that, and so forth. So that is what you are looking for. You want to look for the sign. What is the sign? Is the sign positive? Is it negative? Or is it undefined? Because it might happen that we have an undefined. So if we are actually having an undefined, let's say before we start with an undefined, we're actually not getting a negative, we're actually not getting a positive, we are getting a 0 throughout this interval. If we are having a 0 throughout this interval, we actually end up having to check that the function is actually increasing. So if it is increasing, it is increasing at a constant. So this one, if we are, let's say we are having a 0 here instead of a plus or minus, it means the function is actually constant like this, but it is increasing if your f prime is greater than 0. But if it is less than 0, which means your function is actually decreasing but at a constant rate. But if this one was also 0, which means the function there was actually constant like that. So that is what is important. Once we have an undefined, then we have nothing to report about the function. We have to check other areas because there is nothing in that interval because it's undefined. So there's nothing in that interval. Now we go to the fifth step. The fifth step is just saying that then the open intervals will tell us the intervals where the functions, the function f is concave up or concave down. So that is actually what is actually going to happen. The same thing here. Where's this? The first derivative test here that we're doing. If let's say here you are actually having a 0 throughout this interval, it means actually the function is actually constant throughout this interval. And also the same thing if you are having an undefined here, which means the function is not increasing, is not constant, and also is not decreasing, so there is nothing to report in that interval. So those things are also important here. You are checking the sign, and also you are checking is it defined or not, and more importantly, are we actually having a 0 throughout? So those are the most important things that you want to report on when it actually comes to this number line here. So why these things are important, we have 4 minutes that we can kill. Why these things are actually important here. I'm just gonna give you a little bit of a sketch here because I'm going to stop here. Why these things are important of knowing first derivative, second derivative, and third derivative, and fourth. So when you are plotting a function, the first thing that you need to know if you wanted to have a right plot, the first thing that you need to know, you need to find the x and y intercepts, and then you mark them in the Cartesian plane. And then secondly, you want to know the intervals whereby the function is increasing and where the function is decreasing and where the function is actually constant. That is why you want to find the first derivative of that particular function and the first derivative test. Once you have increase, decrease, constant, and undefined, you want to know the points whereby the function is either concave up or is it concave down. So once you have those things, or is it just constantly increasing or constantly decreasing or constantly actually flat there, so you need the second derivative test and those points. Once you have those things, of course you know that I can just end up evaluating the outputs of each of these points, and then I can actually draw the smooth curve because I am actually having a complete analysis of what is happening in between 0 and some finite points from negative inside. And then the last thing that you will want to understand now, what will be the limit as x approaches positive infinity of this function. And then you also want to find out what is the limit as x approaches negative infinity of this function. And then once you know this and that, you can completely draw your functions because you know what is happening at infinity. You have a complete analysis of that particular function. I hope the theory part of things have been covered, and now we will be able to start at the actual examples of actually how to actually solve realistic problems, not only theory, and that will be in our next lecture, which is going to be lecture 44. So that is what is going to be important. And of course, like I said, I will just write the steps of how you plot a function and give you up front. And then of course the plotting is not part of what we are doing, it's not part of the syllabus, but I want to give you this in advance. And then we'll deal with the problems whereby the question is saying find the intervals where the function f is increasing and where the function is decreasing. I will give you some problems, 5 of them. And then the second part that we will do, find the interval where the function is concave up or down, and I will give you 5 problems there. And then the next thing that we will do, I will give you 5 problems on how to solve optimization problems. Of course, I will give you a summary of the steps that you need to follow to deal with optimization problems. And then once you can do that, I think we will just close the lessons that revolves around derivatives, and then we focus on integration entirely, so that by Sunday at least we are completely done with some things, with the things that will be included in your test, probably, if possible, with everything that will be included in your exam, and then see how much you got and how much you understood in all these particular lessons. The lessons that are under lecture 43, all of them are actually revolving just theory, not much of examples. So just pay a little bit of understanding there, take some notes, and make sure that at least you have a complete understanding of the theory behind, so that when we are dealing with problems, you really understand what we are doing. You're not just writing everything, because it becomes even difficult if you don't know why are you doing this in the first place. I think I will stop